Hello, everyone, and welcome to today's webinar, HashiCorp Vault and Google Cloud, Managing Security in a Containerized World. Please feel free to type your questions during the webinar. We compile all questions and answers at the end of the webinar and send the results to everyone who registered. This webinar is recorded, and the recording will be made available after post-processing, usually within about 2 days. With that, let's go ahead and get started with Brian from our team.
Hey everyone, thanks for joining. I'm Brian Kassouf. I'm a software engineer on the Vault team. I've been on the Vault team for about a year now, and I'm on Twitter at Brian Kassouf and GitHub. And today I wanted to talk about a few high-level topics. First, I want to cover some of the use cases of Vault and just a really brief introduction into what Vault is. Then I want to talk about some of the new features that came in Vault 09, which released yesterday. And then lastly, I want to talk about the Kubernetes authentication backend, which came out in our last release, 083. I want to talk about how it works and do a brief demo of it. So some of the common use cases we see for Vault are secrets management, which is essentially this problem of your applications need all of these things before they're able to run. They potentially need some database credentials or a TLS certificate so they can bootstrap their HTTPS server. API tokens for various services, access to cloud providers, and so on and so forth. And so this problem is how do we get these secrets to the applications securely and efficiently? Also, a common use case is identity and access management, which is essentially this problem of how to govern access to what secrets people have access to. So this is how to get human operators involved and give them access to maintain and read secrets. And lastly, encryption as a service, which is a problem that has a whole set of subproblems. So this is how to do key management, how to do key rotation, how to gate access to keys, and make sure that everyone who's using the encryption and decryption key are privileged. Also cryptographic offload so that end applications don't have to implement cryptology themselves. So Vault provides a very high-level API to allow you to encrypt, decrypt, and HMAC any type of data. So some of the problems Vault tries to solve are this idea of secret sprawl, which is essentially within your organization, you might have your secrets spread out across many different areas and locations. They might be checked into Git. They might be on your host's file system. They might be in people's brains. Maybe everyone in the organization by default knows the root database password or something. And another issue is the management of these keys are generally decentralized. So there's not one entity managing all the life cycle of all these keys. So it's really hard to see when the last time it was rotated and how to actually go through this rotation process. Additionally, there's limited visibility into how these secrets are being used, and there's not a clear audit trail of how they're being used or when or by whom. And lastly, there's a poorly defined break loss procedure, which is essentially when a credential needs to be revoked for whatever reason. How do you do that quickly and efficiently without breaking your existing systems? And so some of Vault's goals to address some of these problems are being the single source for secrets. So Vault wants to keep all the secrets organization needs in this very secure, encrypted at rest, encrypted in transit application. And Vault also provides programmatic access. So how do applications gain access to secrets? And Vault provides a number of authentication backends that work with applications. So some of them are application role, Google Cloud, Kubernetes, AWS, TLS, and so on. Also, we need to figure out how to allow humans and operators to access secrets and manage them. So there's also a number of authentication backends designed for humans to use. So there's user password, there's GitHub, there's LDAP, there's Okta, and many more. So additionally, we want Vault to be a very, very practical way to do security. We want it to be easy to use and not so onerous that people go around the security. So we provide an easy-to-use HTTP API that comes with an ACL system built in so that you can very granularly define who has access to do what. And then it also has built-in auditing so that every request and response can be automatically audited. And then lastly, we want it to be modern data center friendly, which essentially means no hardware requirements, because oftentimes Vault will be running inside of a cloud provider where you don't have access to the hardware. So that was a very brief introduction into some of the features of Vault and some of the goals. But now I want to talk about some of the new features that came in the latest release of Vault, which is Vault 09. And this came out yesterday. So the first new feature is identity. And some pieces of identity have been around for a little while, but they were in our enterprise offering. And so with this release, we moved them out into open source and added a lot more functionality around them. And so identity as a whole is a system for understanding the identity of a person or system across all of their logins and all their tokens. And then once we have all this information about who this entity is, we can use it to create more finer grained access control and policy decisions. So within identity, there are a few different objects. So we have an entity, which represents this single person or system that we keep track of across all their logins. And so you can assign specific policies and metadata to an entity. And then we also have aliases, which is the mapping between an entity and one of their credentials in an authentication backend. So for example, over here we have entity Bob. And Bob has a number of aliases. Bob can log in through LDAP. He can log in through GitHub with his GitHub user. He could use an X509 cert. And with identity, no matter which way Bob logs in, he gets correlated back to his entity and automatically gains all the policies and metadata that are assigned to his entity. So within identity, there's also groups. So groups are a way to manage the identities by placing them into this hierarchical set of groups. And groups can contain both entities and other groups. So over here on the right, we see we have an engineering group with some set of entities. We have team 1 with some set of entities and team 2 with some set of entities. And then each team also has, each group also has their own set of policies associated to it. So all the policies within a group are inherited by the member entities and the member subgroups. So for instance, if you're a member of Team 1, you have all the policies and metadata from your entity. You also inherit the policies and metadata from your team, so Team 1. And then you also inherit all the policies and metadata from any team that is a parent of your team. So you would also get the policies that are associated to everyone in the engineering organization. So there are also group aliases. And group aliases is mapping from an internal group within Vault, so for example, Team 1, to an external group from a third-party authentication provider. So for instance, we can say in LDAP, where we have our group structure already set up, if you're a member of Team 1 in LDAP, you automatically become a member of Team 1 within Vault. And so it's a way to import your group membership from external services. And so Vault will automatically add this user to the identity group, and they will automatically inherit all the policies and metadata of that group. So currently, this is able to be done with the LDAP backend through using LDAP groups, the GitHub backend using GitHub Teams, and the Okta auth backend. And so for us, identity is a really core feature. It not only makes managing the users of Vault much more simple, but it also is a good feature that other features can be built upon, because now we have this sense of who someone is within Vault. We can make much more powerful features. One of which is control groups, which is a premium feature within Vault 09. And control groups use identity to enforce a multi-person rule through policy. So some examples of what you can do with control groups say something like, anytime a user reads the secret foo, require that 2 people from the managers group approve this request. It can also be done on write requests. So you can say, anytime a database configuration is updated, require that 1 person from the DBA group and 1 person from the security group approve it. So the control group workflow ends up looking something like this. A user will try to read secret foo, but Vault will recognize that a control group policy has been set on that secret. So they, instead of returning the actual secret data back to the user, Vault will return a response wrapping token. And within Vault, a response wrapping token is simply a token that can be used at a later date to retrieve some set of data. So it kind of wraps the data with this token. And it's a single-use, one-time only token. And so this response wrapping token is a little different in the sense that it can't actually be unwrapped until the request has been authorized by the set of people who have been defined to authorize it. So the user will hold on to that token. Then they will pass on the accessor to the various authorizers that they need. And the authorizers, once they have the accessor, can either choose to authorize a request by making an API call to Vault, saying we allow this along with the accessor that was given, or they can decide to deny the request by using the accessor to revoke the token. And so once the request has been authorized by the various parties, the initial user can now take that token that was given back and tell Vault, okay, now I want to unwrap this. And Vault will verify that the request has been authorized, and if so, it will return the response data. So here we can see we get back bar equals speaking. So the way you can configure control groups is one of 2 ways. You can either set an ACL policy by writing an HCL file, and you can define the path you want it to work on, and then you add this control group block, which also takes the names, the groups that you want authorizers to be in, and the number of approvals. So for this example, we require 1 approval from someone in the managers group. Alternatively, you can use Sentinel, which is our policy as code framework, and you can write in the Sentinel language to define your policy. So here you can import the control group package, and you can loop over all the authorizations and verify that each one is appropriate and enough have happened to allow the request. So another new feature within Vault 09 is a pro feature. It's called Auto Unseal, and it can be used with GCP Cloud KMS. So a little background is when Vault starts up, it has to go through this unsealing process. And this is because Vault's data is automatically encrypted at rest using AES GCM 256. And before Vault can start up, it needs to be able to read its data, so it requires the decryption key. And this decryption key must be provided online. So after Vault starts up, the encryption key must be handed to it. And we want it to be this way because we don't want the encryption key to just be unencrypted in like a config file or in your configuration manager. Because this decryption key is the keys to decrypting the rest of Vault's data. And so how this is traditionally solved is using this Shamir secret sharing algorithm. And so how it works is we create an encryption key, and then we protect that by encrypting it with a master key that we create. And then we take the master key, and instead of storing it somewhere, we split it into n number of shares. And we tell Vault we require t number of shares to come together before we can recover the master key. So by default, Vault splits it into 5 pieces and has a threshold of 3. And so when unsealing, at least 3 of your key holders, which are generally people throughout your organization who own one of these key shares, need to come together and provide their key share to Vault. And once Vault gets 3 of these key shares, it's able to decrypt the master key, which can then decrypt the encryption key and then continue normal vault operation. And so with GCP Cloud KMS Auto Unseal, it works in a somewhat similar way. We still create an encryption key, protect it with a master key, but then instead of sharding it, we encrypt that master key with Cloud KMS. We store the encrypted key locally, and then when unseal needs to happen, it just simply takes that encrypted master key, decrypts it through Cloud KMS, and then we're able to use that master key to decrypt the encryption key and decrypt the rest of the vault. And so another nice feature of the auto unseal is it also provides recovery keys for fallback, which are the distributor shares. So the way to configure this would be to add this seal block to your config file, and you say seal GCP Cloud KMS. You give it the project name, which is Vault Project in our case. You give it the region where your keyring lives. You give it the keyring name and the crypto key name. And credentials for GCP can either be provided in this config or through the instance service account if you're running on GCE or GCP. And it should be noted that the service account that has access to this keyring should be very strictly locked down and audited, because with it you can decrypt the encryption key and therefore the rest of Vault's data. So another new feature came in Vault Premium is called Seal Wrap. And with Seal Wrap came a FIPS 142 compliance letter. So Seal Wrap is functionality within Vault that allows it to encode the critical security parameters with encryption that's derived from external modules. And these external modules end up being the auto unseals that we have. So HSM, GCP Cloud KMS, and AWS KMS. And it allows Vault to operate at the FIPS 142 level of the crypto modules that are used in the auto unseal source. And there's if you're interested in more information about this, there's a lot more info on our blog post, along with a link to the compliance letter. So next I want to talk about the Kubernetes auth backend, and this is what I'll be talking about the rest of the talk. And this authentication backend came in Vault 0.8.3, which was our last release, and it's in the open source version. And so the Kubernetes auth backend works by binding Kubernetes service accounts to a Vault role. And Kubernetes service accounts are an internal thing within Kubernetes. And then it uses the Kubernetes token review API to validate that these JOT tokens are valid. And then the nice thing about this auth backend is it doesn't need any external pieces to be running within Kubernetes. It's simply Kubernetes service accounts, which are an internal built-in thing into Kubernetes, talking to a built-in Vault backend. And so the way it works is you tell Kubernetes that you want a particular service account mounted to your pod, and Kubernetes will automatically add this service account token into a temp at best volume onto your pod. And so once the service account is there, your application can read the service account from local storage. It can send the JOT along with the role name up to Vault. And then Vault will validate the JOT is valid, and then it verifies that the service account that's defined by the JOT is authorized to use the role. So its name is valid, its namespace is valid, and it's exactly what we expect. And so then Vault will call out to the Kubernetes token review API to validate the JOT is still valid, it hasn't been revoked. And if all that succeeds, Vault will return the token to the application. And if that fails anywhere along the way, Vault will reject the authentication requests. So the way to configure this would be, first you need to enable the authentication backend. So you'd call Vault auth enable Kubernetes, which tells Vault we want to start using this auth backend. Please mount it for us. And then to configure the backend, we call the auth Kubernetes config endpoint. We give it the token reviewer JOT, and this is a service account token that is that's sole role is to validate other JOT tokens that are passed into this backend. So this is telling Kubernetes that we have an identity of someone who's allowed to validate other tokens. And so if you're using RBAC roles, this token has to be able to access the token review API. And then we also pass it the Kubernetes host and the Kubernetes CA certificate so that we can know where the Kubernetes API lives. Then we also configure a role next. So we'll hit the auth Kubernetes role demo, and that means we're making a role named demo. And then we'll pass the bound service account name, which is essentially the name of the service account we require to access this role. So we'll say vault auth. Then we will create a bound service account namespace, which is the namespace we require the service account to live in. And so for this example, we'll just do default. And then we also give it a set of policies. And the policies are will end up being attached to the token that's created through this role. And those policies map to a set of capabilities and access within Vault. And then we also provide some token settings. So here we can say we want our token to have a period of 60 seconds, which essentially means you need to renew this token every 60 seconds or else it'll expire. And so now that we've configured the backend and we've created a role, we can use it to log into Vault. So to log in, you'd hit the auth Kubernetes login. You pass it the role name we defined, which was demo, and then you pass it the job. And if all this succeeds, you'll see an output similar to this with your Vault token and a bunch of metadata around the token. So I want to switch over and do a very quick demo of some applications using this backend to authenticate to Vault and get a Vault token or get some set of secrets. All right, so I have a Vault server already running, and it's actually was configured to have the Kubernetes auth backend set up, and I used almost exactly the same commands that I just showed on my slides. So the first thing we need to do when using this backend is to create a service account token that we can use with it. So over here we have a YAML file that just defines our service account. So our role is expecting a service account named vault auth in the default namespace. So that's what this this YAML file defines. So now we can go over to Kubernetes and create service account. So we've done that. So now I can show you the deployment file for the application we're going to run. So you can see that we define the service account name as vault auth here, which is the service account we just created. And then we have one container running our application, and we also provide it with the vault address. So here's our actual application. It's pretty simple, only about 60 or so lines of code. It first creates a Vault API client, which is this is a Go application, and so we provide a Go library for our API. And then here we're just simply reading the Kubernetes service account token from that temp.fs drive that's been mounted. And then we call out to the Kubernetes login endpoint, passing along the role name demo and the job. And then down here, we'll just simply prove that we got a token by logging it out. And obviously, you don't want to log out secrets into your logs in production, but this is for demonstration purposes. And then below, we will just simply loop forever and renew this token every 20 seconds or so that it stays valid for the lifetime of the application. And then once this application has this Vault token, it can use it to access any of the functionality within Vault that it has permissions to. So it can maybe grab some database credentials, or it can get a TLS certificate to bootstrap an HTTPS server, and so on. So we can go over here. see that there are no pods running. And we can run the deployment, and then we can read the logs, and we can see that we successfully got a vault token. Here's our little warning message. And then down below, we can see that we started to renew the token. So about every 20 seconds, we should see a new entry coming into here saying that the token was successfully renewed. Cool. So I have one more application to show you. And this one is slightly different, but still pretty simple. We have a service account name, which is vault auth. So we're providing our service account to the pod. And then here you'll notice we have two containers running. The first with our application, and the second is a container running console template. And console template is a tool that knows how to talk to Vault, retrieve some secrets, and template them into a template file or a config file. And so in order to pass this config file that we're going to create between console template and our application, we'll create a volume that both containers have access to and use it to have console template write the template and our application read it. And down below, we can define that this volume is in memory only, so our applications are never actually being written to disk. So here's our application. It's pretty simple, pretty short. It really just starts up and tries to load the config file. And if it does, if it finds the config file, it simply logs out what was inside of it. So we should see something. We should see a username and a password that we got from Vault. And this is the script that will actually start up console template. And this is where we're authenticating to Vault. So here we're just retrieving the service account token from disk. Then we're making a curl request to Vault's API, providing the role name demo and the JOT token. And then down below, we will start up console template, giving it that token. So if we go over here, we can create the deployment. We can see that there's an extra pod running with two containers in it. And then we can look at the logs. So now we see the error message that we had in our application, and we see username demo, password test. And so console template went to Vault, got these credentials, templated them into a template file, and our application read that template file and outputted it. So this is a super handy way to provide credentials to applications that can't know about Vault or don't know about Vault, and you can provide credentials through a template file or a configuration file. Cool. So that's all I had for you. Next up is Emily Yee from Google, who's going to talk about more GCP and Vault integrations.
Hi, I'm unmuted now. Sorry about that. Yeah, so thanks to Brian for the introduction. I'm Emily. I'm a software engineer at Google, and I've been working a lot with the HashiCorp Vault team on some awesome features that I'm excited to talk about. So Brian's given a little introduction about what Vault is, so I'll give some background on Google Cloud Platform, or GCP, and how I got involved with Vault. So Google Cloud allows you to run your applications and workflows on the same infrastructure used to power Google. We focus on scalability, reliability, and security for our services so our users can focus on building their own products. And our high performance and pricing models speak for themselves. I have a quick overview of some of the things we offer. So we have compute products like Compute Engine, VMs, or our container services, GKE. And we also offer fully managed app development platforms like App Engine. We offer reliable, scalable storage options like GCS, our blob storage, or Cloud Spanner, our strongly consistent relational database service. That was actually publicly launched earlier this year, but we've been using it internally at Google for quite some time, so I'm very excited about that. We also offer products for managing the huge data sets generated by modern applications. We offer BigQuery to make data processing easy and management free, and our product DataProc makes open source data tools like Spark and Hadoop hassle-free. Speaking of open source, we really do love it at Google. Google is founded on incredibly popular open source tools like Kubernetes and TensorFlow, and we think OSS is good for everyone. That's actually how I get to work on HashiCorp Vault despite being a Google employee. Our team was formed because my manager, who worked on Compute at the time, kept having conversations in the community where engineers at other companies building great open source tools were getting requests to support GCP features, but they just didn't have the resources to do so. So he grabbed a couple other of 20%ers or part-time engineers who just started contributing to open source projects. And they were so successful that Google just greenlit a full-time team. Now we're about 12 engineers working 100% of the time on open source software. Part of our earlier work was with Vagrant and Packer, and that really paved the way for our partnership with HashiCorp. Customers really love the HashiCorp toolchain, and we've made a lot of happy GCP customers as well from working together with HashiCorp. As a Google employee, we have the benefit of being able to directly talk to other teams on GCP and support early access features as soon as possible. For example, one of the GCP features I'll talk about later was actually launched the same day we launched the Vault integration that uses it. So we currently have full-time engineers on both Google side and HashiCorp side supporting Google integrations into HashiCorp tools. For example, Terraform, HashiCorp's popular infrastructure as code offering, has a Google provider, and we have staff on both sides for that. And this September, I helped to release the GCP authentication background as our first Vault integration. If you're interested in what we're working on, there's a video series on YouTube and several blog posts on our recent work with HashiCorp. We'll send the links out after the webinar, or you can Google it. All right, so just as an overview of my talk, I'll talk about how people use Vault on GCP and how we can improve that. I'll talk about this authentication backend that we released in September in version 0.83, I think, and give a quick demo of it. And finally, I'll discuss on what I'm looking forward to working on next. So why are people using Vault on GCP? A lot of GCP users are interested in Vault, as Brian mentioned, for secret management. You can see some examples of how Vault could help you on the side here. In addition to secrets management, as more companies are starting to think about dividing their apps into microservices and securing communication between them, they consider Vault for PKI, for service-to-service authentication. Google's actually doing a lot in this space, including work on an open source platform called Istio, and which is for managing and securing microservice infrastructure. And Vault has come up a lot in this discussion. I'll be focusing mostly on the secret management side, but our example would also work for PKI as well. So this is typically what we saw when we asked people how they're running Vault on GCP. People usually start their Vault server in GCE or GKE, although the second case is a lot more complicated. When you start a Vault server, you need to unseal the Vault using a set of keys, as Brian mentioned. People tend to use things like password managers or just keep it on a file, which is maybe not the best to manage these bootstrapping keys. Um, authentication backend. So once the vault is initialized and unsealed, apps need access to secrets and they authenticate to vault using auth backends. Typically, GCP users were using things like username, password, or LDAP, or Okta, things that they're already using separately, but they needed to create a separate identity for each of their GCP entities. Once you actually have an auth token, you can start generating secrets. You can just save generic secrets like API keys or do things with database credentials. Any secrets you do save will be encrypted and saved, as Brian mentioned. And then these are stored in whatever storage configuration we want. While GCS is actually an option here, a lot of people weren't using it. They typically chose something that actually is available in high availability mode. GCS backend was contributed, I think, before HA was made available in GCS. So that's potentially a reason why. And so one of the advantages of Vault is also that accesses to secrets are audited. When we talk to customers, usually they weren't even sure what audit backends they were using. Typically, they just dump out their logs to cloud storage and then don't integrate them into their monitoring pipeline, which kind of defeats the purpose. And so what are some pain points with this setup? As we mentioned, authentication options, you have to create a separate auth identity per GCP entity. When we have perfectly good IAM identities or IDs. More credentials to manage outside of Vault, and in general just kind of defeats the purpose of having Vault. Unsealed key management, as we mentioned, pretty much everyone we talked to had a problem with this. To unseal Vault, you need a certain set of keys, as Brian mentioned, and there was a lot of manual work involved and a lot of just confusion about where should we store these keys. And so the things we heard were sort of like one DevOps person has all of the keys and they use it. And so that's really not ideal. Finally, Vault is self-managed. So since it's not a natively hosted service on Google Cloud, you still need to run the server yourself and do failure recovery yourself. So a lot of the work that the Vault team and I have been doing recently have dealt with these issues. For example, Brian talked about the unseal feature coming out in the new version of Vault, and the main feature I'll talk about, the authentication backend, will address the first pain point. So this is what a best practice deployment looks like now. We'll focus on the case where you're all in GCP and running a single shared Vault, but this deployment can vary, but this is the one we'll focus on for this webinar. So you start your server up in Compute Engine or Container Engine. You can store your secrets in cloud storage. Your audit backend, so you can either use the file audit backend or the syslog backend. Either one has easy hooks to be ingested in the Stackdriver monitoring, which is actually, and logging. And so you can easily integrate your Vault alerts or metrics into an automatic GCP resource-wide monitoring pipeline. Unseal is still a hard problem since it is a root bootstrapping secret. As Brian mentioned, the new feature in Vault 9.0, you can now have the automatic unseal. But if you don't want to use Pro, you can still store it in GCS encrypted with Cloud KMS key. And finally, the auth backend. This is what I'll focus on for the rest of the talk because I worked on it. This authentication backend allows you to authenticate either IAM service accounts or compute engine instances. So let's talk about that. So IAM service accounts are sort of a core identity in GCP. This auth message is useful for users, for general service accounts, or for arbitrary applications like App Engine apps or things like that that don't necessarily have an identity set up. GC instance authentication only works, of course, for the VMs within GCE or GKE. but it allows you to easily obtain a vault token without needing further authentication, and you speed up automation and secrets access greatly. So I'll give a little background on the GCP auth backend. So you can see an example of authentication command here. This looks pretty much like the Kubernetes one. So you provide two arguments. The first is the role. So the role binds a policy or what secrets you can access to authorized entities. Each role has different restrictions based on the entity being authenticated. So for IAM roles, we restrict it by server's account ID or email. And for GCE roles, we restrict by things like instance group. What instance is an instance in the instance group, for example? Labels, zone, region, or service accounts that are linked to the instance. Provide the public key to Vault when it needs to verify it. However, this kind of defeats the purpose of not having to generate a key for your service account. Google, if you use the IAM API method, Google has their own system managed service account keys that are never revealed to the public and rotated automatically by Google. With GCE instances, this is actually the new feature that I mentioned earlier. So now you can obtain an instance metadata token from the metadata server, which is automatically available to the GCE instance once it starts up. So I'll go into a demo very shortly, but this is essentially how you would set up your Vault auth backend. So you enable the GCP auth backend using the first command, and you write credentials. These are just credentials that need read-only access to GCP APIs, IAM, and GCE. This just means like, can I look at the service account and make sure it exists? Can I get this instance and make sure it belongs to this instance group? Things like that. And finally, you create two roles. Or I created two roles. The first one being an IAM role, and the second one being a GCE role. You can sort of see pretty similar to the Kubernetes auth backend, the sort of arguments that you provide, things like policies and project ID is the GCP project, and then the bound service account or bound instance group is what I'm going to use for my demo. So let's show how authenticating IAM service accounts work. So originally, whatever service account you need to authenticate with, you create, and you send a request to IAM for that. Once you have that service account, you can create a role that allows you to authenticate under that service account. You then, whatever user has permission to sign JOTs for that service account, will send unsigned claims to IAM API, and it returns a signed JOT. This JOT expires within at most 1 hour, and we actually enforce shorter times usually. You can configure this in your role, but the default is 15 minutes. This is just because we want the JOT to essentially be used once per authentication attempt. So you basically want to treat it as like one use only. Once you have this signed JOT, you can send an authentication request to Vault using that JOT. Vault will verify the token signature by obtaining the service account public key from Google IAM, and then return an auth response if everything works out. So I'll go into my demo now, but just as an overview of what I've done, I'll use the gcloud tool to sign the jot, and I will log in here. So this is my server. As you can see, my IAM role that I wrote here is here. This is a secret that I wrote earlier, vault read secret foo, and essentially it just says zip equals zap. And then finally, I created a policy. This is what I mentioned, where it's essentially gating what secrets you can access. And so you can see that I should be able to read a secret foo using that. So right now, if I try to do it without a client token or an auth token, it will give me an error. So this is a script I'm going to use to generate the token. You can see I'm just generating the claims here, and then I'll run the commands as I mentioned. This is the generated claims I created. I'm going to now sign that. So now that's signed, and it returns the signed jot in a file and shows you the ID of the key that was used. So now I'm going to run the authentication step. So now this token that you see here is the returned auth token. And now I should be able to do that and hopefully read the secret. Sweet. So that's how the IAM auth backend works. Going back to the slides, I'll go through the GCE authentication backend or workflow now. So the first thing you do is on the VM, you request an identity token. This token is returned and it's a signed jot. You then just send this to Vault, and Vault will verify the token signature and then make any other calls to compute engine that it needs to make sure the instance is still running. If it's restricted by instance group, whether it's in that instance, whether it has the labels and is in the right zone or region, things like that. Finally, once it verifies all of this, it will return the auth response. So a couple notes, GCE tokens can actually be used to authenticate under IAM roles as well. You can see an example of what the jot looks like. So the subject here is actually a server's account that is linked to the token and to your instance, and you request a token based on that server's account. But you don't actually need to authenticate or do any further authentication step to do that. The other thing to note is that the audience claim that I would specify is a optional field on the JSON web token. We require that it ends in Vault and whatever role you're trying to log in as. GCE actually requires that you specify a protocol as well when you generate this token, but we ignore it. So I'll show you an example of this. So I'm actually going to create an instance group from a template. So the startup script will get instance identity metadata from the metadata server. It'll authenticate to Vault, and then it'll read a secret. I don't know why I said read the secret there. So curl, you can see this is what the curl command looks like to get the metadata. You can see my audience. I have this fake protocol at the beginning, and then the Vault and whatever role I'm authenticating as, and then the format. This is required to actually get the information earlier about this like Google Compute Engine part of the token. So yeah, so I'll actually do the demo now. So this is my Vault server again. As you can see, this is the role that I wrote. It requires an instance group and the zone. And then you can see that the secret and policy that I wrote earlier are also here. I'm going to close that. And so this is my template. I'll go over the startup script that I wrote. So as you can see here, the first thing I do is I get the metadata token from the metadata server. Notice that this doesn't really need any other tokens or things like that to authenticate to the metadata server. Then I write it out to a payload, and then I do the authentication request here. And then once I do some JSON parsing here and make a request to Vault to actually get a secret. So we're going to create an instance group. As you can see, the instance group name that I want is secret instance group. So I'm going to do that. And then I specify that I want everything to be created in West 1A. And then I will create this. So we'll wait for that to spin up. Oh, that may have not worked. Oh, it seems to be not working. Let's try that one more time. Huh? Oh, so let's actually try a different region. So I'm going to write say zone equals US East 1A. So I'm going to try that again in a different region. Or is 1A actually the same? No, it's not. Okay. Central 1A then. Cool. So let's see. I have the template set up and the group name set up. Nope. Okay. It's just not going to work. Sorry, guys. Well, in any case, this is basically what you would do, and then you would see that the secret was saved as a temp file on the server. It might be a quota issue. I may have run this demo a couple too many times. Yeah. So I guess going back to my presentation, just in conclusion. So things you might want to consider when you're deploying GCP. So are you doing multi-cloud or hybrid deployments? Where do you want your source of truth to be? What will you use to authenticate, and what you can use your authentication options to essentially generate credentials for all of your different cloud options. Are you running different instances of Vault? Do you need one for secret management versus PKI? Are you going to run a different Vault for every single cloud option that you do? This is less common, but we still see it sometimes. Do you have Vault servers as a critical part of your infrastructure that other services rely on, or is it spun up per service? Things like this. One of our solution architects, actually, Dan Isla, recently wrote up a solution for deploying Vault with GCP, and you can look at that. It's linked at the end of the talk. Overall, this sort of gets at where do you want the root of trust for your secrets to be. We could potentially make Vault the root of trust and generate credentials with necessary permissions as needed, and just use a server's account initially to authenticate that doesn't actually have that many permissions. Which actually brings me to what I'm working on next. So I'm really pleased to start working on this. I'm going to be working on a secrets backend. How could this be useful? Let's say in the demo that I actually needed to grab a file from a GCS bucket, So I don't actually want to have the service account that has access to my GCS bucket to live for very long. But how else do I access it? Well, then, in this case, what I could do is actually ask Vault to generate a short-lived service account for me. Vault would essentially use the secret backend to create a service account, set all the policies required on it, and then return whatever credentials they need. And then once the Vault lease is up, it will just delete it as needed. You can look at a GitHub issue 1052 for updates on this, but otherwise feel free to drop a line on GitHub if you have any thoughts on this. It's actually a fairly hard problem because policy setting in IAM is not fun. It is per resource per API. So essentially, if I want to set policies on several different resources, I have to call out to a different API potentially per resource. How do we want to represent this in Vault? While Terraform actually has a lot of access to every different GCP API, we don't actually have something like this set up in Vault yet. So how do I want to parse policies per resource and then for each of those resources call out to the APIs required? And then another pain point that actually involves the auth backend. There's no easy way to determine if the service account has a role. You could see how potentially it'd be easier to restrict IAM roles by, or IAM Vault roles by GCP roles. So you don't have to actually have the service account ID or email available before you create the role. However, it's very hard actually to determine what service account has what role on a resource. So if you have any thoughts, please feel free to get in touch. I think they'll send out our contact information after. These are also some of the blogs and docs that we've been working on. Thanks everyone for coming to the webinar. Thanks for the Vault team for helping me with my integrations. And I guess that's my talk.
Thank you, Emily, and thanks for the great presentation. I hope everyone enjoyed today's webinar and was able to learn more about how Vault integrates with GCP. Thank you, everyone who joined, and a big thank you to Brian and Emily for presenting. I also want to mention that HashiCorp is hiring, so if you liked what you heard today, please take a look at our jobs page at hashicorp.com/jobs and see if there might be a fit for you. And finally, as I mentioned at the beginning, the webinar was recorded, and we will make the recording available on our website after processing. We will send an email to everyone who registered with the complete list of questions and answers after we summarize all that data. You can also keep your eyes out on Twitter, where I'll post the recording link a little later today. Have a great day. Goodbye, everyone.